Live. We are now live on YouTube as well. Attendees starting to trickle.
Hi, everybody.
How's it going, everybody? Thank you for coming to the Tezos workshop with Mike. We're super excited to have Mike here from the Cryptonomics team, talking about Tezos and building with Tezos. Again, like we said before, this is a multi-blockchain. There you go, even better. I love that. This is a multi-blockchain hackathon here, where we have Tezos, we have Polkadot, we have Ethereum, and this is going to even deeper than that. Tezos has some fantastic prizes, so definitely pay attention. Definitely stay tuned to everything that Mike's saying here, because he's going to teach us a lot of really cool stuff. So, Mike, welcome. Thank you so much for joining us.
Thank you for having me. So yeah, I'm Mike from Cryptonomic. I'm also on the judging panel, but I'm a lot more excited about doing these workshops to teach you guys how to work with Tezos and how to build blockchain applications that are useful and usable by regular people. I myself have extensive experience in traditional finance for quite a while. I'd like to thank Chainlink for allowing this opportunity for us to present our toolkit and Tezos to you. But let's talk about Cryptonomic and blockchains and why we do it trustlessly and stuff like that. So let's go. We are a company committed to these very difficult words and even harder concepts. We are blockchain agnostic, although a lot of the public work we do is based around Tezos. Fundamentally, though, we'd like to make all blockchains, easier to use and more popular, more useful for more than just trading. To that end, we create development tools, we create documentation, and we host events. We're a small core team based in Bushwick. Lots of hipster cred there. If you guys are not familiar with that neighborhood, that's in Brooklyn, New York. Although I don't know if our office is still there. I haven't been there in 6 months. Right, we have extensive cross-domain expertise, not just finance. We have a requisite PhD on staff. I'm not one of them, so I just contribute snark, so I get to present. We have been building for quite a while, and I want to make sure you guys remember our name. I like to think that we bring discipline of experience of product delivery to blockchains. Since inception, we've built developer tools, we've created infrastructure to run blockchains, we've built tons of documentation. And more recently, we have started to build on blockchains, and we're going to talk about that during this presentation. So yeah, I like to think that we add magic, and let's talk about what I mean by that. So this is Galleon. It's our wallet for the desktop. We have it for Windows, Mac, and Linux. It's being distributed through the app stores mostly now. It's also a smart contract UI. We have Galleon Mobile. These are iOS screenshots. I swear I have an Android build any day now, or week, probably. MinionX. MinionX is our blocky explorer. I don't know if you guys are familiar with Minitel, but just like Minitel, Tezos is a French origin technology project, so we figured the design was quite appropriate for that. Another thing we've built is Aranex. This is a dynamic chain data reporting and analytics tool. So I'm showing you a screenshot that I took yesterday of transactions failing on mainnet and the reasons why they're failing. So Aranex, I'm personally excited about because it allows us to cut through the chain data in very interesting ways and discover things about what people are doing and how the chain is being used. But it also turned out to be a very useful developer tool because you can do things like this. You can see how contracts are being called. Like here, for example, I'm showing parameters being passed in. So if you have trouble figuring out how to call a contract, you can see how other people do it. You can see what errors come up and so forth. So this is cool. Final infrastructure, this is Nautilus Cloud. This is our deployment. awareness. Effectively, infrastructure is hard, and if all you want to do is build blockchain applications, you should not run infrastructure. GitHub login. I'll show you that later. Right. So these are products, and they're built on the foundational development tools that we also created. The same development tools that we'll be using today. More specifically, that is Kensei and Kensei.js. Kensei is a modular chain indexing solution. What I mean by that is, well, it's a blockchain indexer, but it is split up into parts. So it can be upgraded and deployed efficiently. It can support multiple chains. For example, I alluded earlier that we are a multi-chain company. Kensei.js is an interface for Kensei where it provides a way for you to submit these queries. So for example, earlier we saw Aranex, and you can open it, aranex.io. There's a front end that allows you to create complex queries. And Kensei.js has APIs to create those queries. In addition to that, Kensei.js supports Tezos. So if you're looking to interact with the Tezos chain, Kensei.js can talk to a Tezos node directly. Cool. So we're going to use this in a little bit, but today, like I said, we'll be building together. And presenting these workshops is inspirational, really. I can't wait to see what you guys do with a pile of cryptographically enabled code. We have limited ideas. There are only so many of us. But when we present to a large audience at hackathons and so on, it's exciting to see new people with new concepts for what blockchains can do for them. But before we get to that, let's talk a little bit about smart contract development. So I don't know how much background all of you guys have in smart contracts and so forth, but you need to be careful. And I think there are plenty of very public examples of why. So definitely read the documentation that's available. And if you had a snag, ask questions. We ourselves are available. Chainlink is hosting a Discord channel for this hackathon, and we're on it. There are all sorts of chat rooms and forums available for you to get help out. And the other thing that I already mentioned in the context of Aranex, but learn from what other people do, right? That's also very important. So another interesting thing about blockchains is that they're intrinsically open source. You can get the source code for all contracts that are deployed and see how they work. If there is an idea that you like and you'd like to understand how they make it work, you can just do that. Yeah. The other thing, don't start from scratch, right? So blockchains have been around for a long time, more than a decade now, and you can build on top of what other people have created before you. You can, if you can't necessarily use the code that they have written because you're deploying a different chain, you can maybe use the concept. Keep in mind, though, that not all concepts are directly translatable between different blockchains. So both Ethereum and Tezos have smart contracts, but they behave differently. They're written differently. We'll cover some of that today. As I said earlier, do not run your own infrastructure. It's difficult and time-consuming, and it's also not your core product. Think about your product. Another thing I've seen people talk about is limitations. Oh, I can't do X on Tezos or some other blockchain. But a lot of the time, there's more than one way to solve a problem. And if you come to a conclusion that there is a particular feature that the platform is missing or Kensei is missing, for example, first of all, you can ask that perhaps this feature is in the pipeline or it can be added. And the other thing is, it's likely that other people came across similar limitations and you can get advice and help them how to do this. Lastly, testing. This can't be stressed enough. You have to test your code. And we're using SmartPy for that. SmartPy is I made a programming toolkit which comes with a rich simulation engine for Tezos. So you can compose your contract in a browser, run simulations on your contract, and then deploy it, all from a single UI. This product is built by Smart Chain Arena, good friends of ours, but this is a separate company. I was working on a game contract a few months ago, and the code seemed fine. And then I ran some simulations, and it turned out that there were certain conditions in which the loser of the game was actually able to drain the entire pool. So that was a bug, and that was a bug that I was able to find specifically because I could run these tests before it's even deployed, which is very cool. But an important thing to keep in mind is that your smart contract, even if it's not buggy, may not behave correctly under all circumstances, and that's important to know. So your code can be fine. It's just that the concept, for some reason, has limitations as far as how people might be calling it. Because once you deploy the contract, you will be attacked. Or let me, if you don't want to use the word attack, you will be probed to see what vulnerabilities you might have. Right, so we're here for Tezos. And what is that really? Let's talk about that. So Tezos 2 years ago was what Ethereum is going to be eventually. Tezos is a proof of stake based chain. Specifically, it's liquid proof of stake. There is this delegation process. Delegation is a way for one Tezos holder to give stake to a validator who will then participate in the block creation process. And there are more details to this that I won't cover today, but we can certainly discuss offline. The validator, they're called bakers because this is a French project, so of course it's bakers. The validators will create blocks and they will be rewarded for it. And there is a social contract, so to speak, on Tezos right now where the baker will share their block rewards with their delegators. So I may delegate to a baker on chain, and they will send me a partial reward scaled to my contribution to them. Now, this process is different from other proof of stake chains that you might have heard of. For example, when I delegate, I am only delegating the rights. I keep the balance. My balance is spendable all the time. It is not locked. It stays with me. So that's important. This process, this delegation process, is central to the on-chain governance flow for Tezos. So you might have heard that Tezos is the upgradable blockchain, and indeed it is. There have been several protocol upgrades over the years. There's one being proposed right now. These protocol upgrades can be anything really. The current one is about reducing the gas costs. Previous one added features. The one before that added features. The next one will be adding features. There's a long, deep pipeline of new things that Tezos will be adding, like private transactions and so forth. So the deployment of these protocols happens via consensus where the validators get to vote. And the idea is that Tezos can be a more stable blockchain, avoiding hard forks because people have seemingly uniformly agreed that the upgrade is a good idea. So that's exciting. And this enables both direct and representative voting, direct voting by validators, representative voting by the delegators. So if I delegate to a baker who voted in a way they didn't like, I can delegate to a different baker next time around. Right, so Tezos is also a smart contract platform, and we'll be doing some of that today. What's special about that? So the base language in Tezos for smart contract development is Michelson. It is a stack-based language. It is strongly typed. These features make it more easily susceptible to the formal verification process, which is effectively a mathematical proof that your contract will perform in the way that you expect it to perform. Like, this is a possibility that's more easy to do on Tezos than other chains. I mean, it is possible, I believe, in some conditions to formally verify solidity contracts, but it is not as broadly applicable as it is on Tezos. There are some differences. So I said it's stack-based one, which isn't necessarily important if you're using SmartPy. Another thing is there are no return functions. There are no returns, I'm sorry, from functions in Michelson. So you have to use continuation passing style. And if you're not familiar with that, this is something you need to consider carefully when you're designing contracts and writing your contracts, because the execution flow will be somewhat different from what you might be used to. But it's important to pay attention to this because security vulnerabilities arise from here. Right, so Tezos is a account-based blockchain. There are blocks, operations, and accounts. We're developers here, so there's also this concept of big maps. That's a storage mechanism on Tezos. We'll take a look at that in a moment on Airnex. If you're using Consay.js, you will notice that when you get block information directly from a Tezos node, it will be shaped a little bit differently when you're asking for the same information from Consay. We normalize the data to some extent once we read it from the chain and the indexer. So this workshop is meant to be hands-on. Usually, well, not in a while, I suppose, but usually we do these things in person. We remove people with laptops, and I'm hoping that you guys can follow along. All the code that we'll be discussing is on GitHub, and I'm going to run it the same way you run it. So should work. Worked last night. We're going to do a couple of things. We'll get a faucet account on a testnet. We'll activate this account. The activation process is simply me saying, hey, I have the private key to this balance. Give me the balance. Key reveal operation says, I'm this account. Here's my public key. This is for cryptographic verification of my signatures. Finally, we're going to make a wallet. What I mean by that really is we'll make an object that stores my keys that we can use for signing. We'll take a look at simple operations like transferring value and delegation, and how we're going to do this. So we're going to be using NPM with TypeScript. Consay.js is also distributed as a Webpack minified library you can use in a browser. We'll be using these wonderful things, Consay.js, SmartPy, and Airnex. And finally, infrastructure. We'll be using Nautilus Cloud. So this screenshot you've seen a minute ago, this is our interface. I'll show you the link in a moment. We have a bunch of documentation. So this link is a collection of articles we wrote about development for blockchains on Tezos and using SmartPy. Then the other thing we're going to do today is, because we're actually going to be deploying contracts and using oracles, we'll be doing that and this. But let's talk a little bit about how you invoke contracts. So you can ping a contract. What that means is you can call a contract with no parameters and no balance transfer. You're basically registering a call. So it's like raising your hand in class, for example. So this is useful because the contract, first of all, can still take action internally. When you call it, it can say, hey, I was called by this address, and the contract can increment the counter, decrement the counter. It can maybe store the caller address in a big map if it wanted to. Another thing that you can do is, because this is a blockchain and the data is always going to be there, you can use a block explorer or Airnex, an analytics tool, to see how many times the contract was called or how many times over what period of time and so forth. I could see this being used as a very rudimentary polling mechanism. You can deploy 4 different contracts for 4 different vote options. I'm not suggesting we're on national ballots on this way, but my point is that you can have a poll. What else? We can invoke a contract. What I mean by that is we can call a contract, again, without a balance, but with parameters. So here we can be asking the contract to perform an action for us or calculation. We can also fund the contract, which may come with parameters, may not, but it will come with a balance. So for example, if you have an escrow contract, you may invoke it with no parameters, but 5 Tez, because you're looking to escrow 5 Tez to this contract. And finally, sequencing. What I mean here is I may call a contract, and this contract internally will call one or more other contracts before completing its execution. This is actually how the Oracle system works. We request a piece of information, and then there's a chain of contract calls that eventually comes back to us. Right, so what I'm trying to get at here really is data storage on blockchains is tricky. You can't really store large amounts. It's expensive, it's slow. And if there may be ways for you to design your application in such a way that you can rely on an indexer, for example, to keep track of the data that you're using instead of storing it directly in the contract. Cool, so we'll be using SmartPy. We have more materials specifically with SmartPy here. This is another collection of Medium articles. I'll let you guys take that down. But finally, let's go. One more QR code. This is blockchains, lots of QR codes on blockchains. This link is the code we'll be running. It's a link to my GitHub to the Chainlink Oracle sample on Tezos. So let's talk a little bit about contract considerations. Permanent deployment. So once you deploy a smart contract, it can't be changed. This is a feature. The idea is that if I'm a user of your contract and you deployed it once and you gave me the contract address, I am guaranteed that this contract will behave the same way every single time because it's immutable. And this is very valuable. Privileged access. What we mean here is that you need to implement this. Blockchains don't necessarily offer you any sort of access control. So one of the most common patterns here is going to be, hey, my admin address is this. A privileged function is being called. Is the caller admin or not? And it's that simple. Unspendable funds. In Tezos, if a contract holds a balance, this balance cannot be withdrawn unless that withdrawal method is specifically implemented in the contract. What I mean here is you have to have presumably a privileged operation that allows you to withdraw the balance to some destination. Previously, if you were the manager of the contract, it was possible for you to simply take the funds. That is no longer the case. Whitelisting. So it's possible that you may want to restrict not just the administration features, but general features of your contract to some subset of users, to your friends, let's say. So you would need to maintain a whitelist. And finally, state rescue. So this is tricky, and I am personally on the fence about this because I don't like this idea. It's a violation of the first bullet here. State rescue is a method that accepts a lambda. It would be hopefully be a privileged access method. But the idea is that if your contract storage is somehow mangled by an unexpected collection of transactions, what you may be able to do with a function like this is execute a lambda operation. And this lambda will modify the storage to a good state. Now, this reduces trust because now you're opening up this contract to the possibility that it will behave differently than expected. I will cover that in a bit. So more considerations. Input validation. This is another one of those things that I struggle with because I don't really like to validate input very much. Why? Because if the contract is being called correctly, then input validation just costs gas, which in turn increases fees that it costs to call this contract. And what you're doing by validating input and providing rich errors to users saying, oh, you did this wrong, please correct it, is not only are you making your contract more expensive to deploy, because strings in a contract will cost storage, store in a chain. Validation is happening every time you call a contract that has to be executed. That costs fees as well. But the people who have read your documentation and are not calling contract correctly will also be paying these fees. So only validate what is absolutely necessary for the correct execution of your contract. Storage. So I said earlier, storage is expensive, storage is slow, it's difficult to use under some conditions. So keep in mind how much and what you're actually storing. We'll be storing very minimal information in the chain. Fractions. There are no fractions. Many reasons for this, but blockchains generally don't implement floating point numbers because floating point numbers can't be easily confirmed across multiple platforms. For example, one CPU fundamentally may represent a float differently from a different one, and this creates problems when you're signing transactions and verifying them. And of course, external state, and that's why we're here. We're going to be using external state with oracles, and that's cool, new, and exciting. So let's touch on this just briefly. I said earlier, state rescue. State rescue, I personally don't do this, and I don't like calling contracts that have it because it allows you to modify the behavior of a contract. So I mentioned earlier that Tezos provides a bunch of this formal verification functionality. That's very useful. But if you formally verify a contract at, let's say, 11:27 a.m., and then you, in order to call it at 11:28 a.m., the contract may change in a way that you don't know in the interim, and this is a problem. Same with arbitrary code execution and Lambda storage. So on Tezos, you can store a Lambda expression in storage and then run it when a contract function is called. Changing behavior, I think, breaks the social contract of blockchains. But in any case, let's come back to this and do the code. So I'll give you guys a second, take this link. Excellent. So I have the code that you guys are probably looking up. There we go. This is the tutorial that we'll be covering today. I see you guys have questions. I will address those questions at the end. Thank you for the link. All right, cool. So this pretty much works out of the box, and we'll demonstrate this right now. There we go. So in the project, we have a bunch of files. One of them is called state.json. So here, we need to provide a bunch of information in order to be able to run the system. And this stuff comes from Nautilus Cloud. Then we'll need a couple of faucet accounts. We're going to be reusing contracts. So the SmartPy team and us have deployed a contract for this hackathon that's supposed to represent Chainlink. It behaves more or less the way a Chainlink contract might on Tezos. There is also a faucet that we'll be using to fund our accounts. Cool. So let's see. We'll cover what that means in a minute. So let's go back to the browser. Let's go to Nautilus Cloud. We want the Tezos node. That's that. We want the Kansei node. That's that. Let's refresh the key. Yes. This is my key. You'll of course have your own. The test network we're using is called CarthageNet. The next protocol is coming up, so that one is going to be called DelphiNet. Network block time 31 seconds. What this means is generally we expect a block on the Tezos testnet to appear in 30 seconds. We're going to wait 31 before we check. Okay, now on to the faucet. Fun. Okay, we're going to just grab this, copy it, and put it here. That's one. And we're going to do one more. All right. Wow, it's really stingy today. Excellent. So now we got the two accounts that we need. Cool, save that document. And this is state.json. This is one thing that would have come to you. So we need a terminal. Okay, so we're using npm, so we need to install our dependencies. If you look at the package file while that's running, npm I will run build. Build just compiles the TypeScript. We write our code in TypeScript. Then we have several example invocations. So first, we need to deploy our system of contracts. I'll explain what that is. Then we will use the client to ask the Oracle a question, and then we're going to use the Oracle to answer that question. This is just a couple of examples of how to call the token contract. So let's talk about initialization. Okay, so we're going to do a few things. These things are based on the content of the state file. So here we have the configuration and accounts, right? So notice that these addresses are blank because we haven't deployed them yet, and the Oracle user Alice and Oracle admin are missing something. So they're specifically missing the secret key. The secret key will get generated once we initialize the account. What does that do? So we take our faucet information, we convert that into a key pair, and we use, that's the wallet I was talking about earlier, so that's the key store. Then we're going to activate the account, which is a blockchain operation. We basically say to the chain that, hey, you know, this is my address, give me my balance. And the balance information is here. So Tezos has 6 decimal places, so this account is going to get 65 and change 1,000 Tez. Right, then we reveal the account, which publishes the public key of the account to the blockchain. This operation has to happen second because it requires fees. This operation is free to activate the account. When you're creating an account on mainnet, if you create an account from scratch, activation does not take place. Activation is the process only for the fundraiser that happened several years ago. So presumably the vast majority of those accounts is already activated. So you only need to activate the faucet accounts for testing.
Hey, Mike.
Cool. So once we,
Mike,
yes.
just jump in here real quick. Could you actually do a quick zoom in on the code? It's a little bit tough to see.
So I actually, can I do that?
So I know VS Code, if you're, are you on a Mac? I know it's like Command Shift.
Apple Plus.
Yeah. Nice.
Close this. So ideally, thank you for that, but you guys can also totally follow along on the website. So I'm looking at this code here. I can just be background noise while you look at that. You don't need to look at me on my screen, but thank you. So at this point, we would have activated our accounts and they're ready to be used. And then we're going to see if we have a token that we can use already. Now, the script comes pre-configured with a token, and we would like you to use this simply because it makes your oracles potentially interoperable, and your accounts can call other oracles. So I can call your oracle if you deploy it, for example. So if it's not there, we would deploy a new token. The code for this is also in the project. So actually, this is a good time to talk about SmartPy. This is the Python code that makes SmartPy work. This is their beautiful website. I'm gonna go here. You definitely need to wait for this to load completely because internally this has a smart contract interpreter and it needs to be fully materialized into memory before it can run. Okay, we're just gonna do that. Cool. So I'm pasting in just the Python code that I have in oracle.py. SmartPy is cool in the sense that you're using Python to develop type-safe smart contracts. It seems kind of weird, but the syntax is something that's easy to understand and is popular. And it is interpreted, obviously, into Michelson that is type-safe. So SmartPy, and I have a bunch of links, by the way, in the README for this thing at the bottom that talk about the various references you can use. So SmartPy has a reference. We have tutorials. There are other places on the internet you can get help from. But let's talk about how this works. When you hit the run button, it compiles the contracts. In this case, there are multiple contracts in this. Ooh, fun, excellent. There are multiple contracts in this file. They will all be built, and the tests will run. So I said earlier that this is a simulation platform. So if you go down, we have tests. And these tests do lots of different things. So here, client one sends a request that gets canceled, right? So this is going to be defined here, right? So here we're calling a function. And you see the inputs and the outputs of this function on screen, and you see how your contract state changes. And then you can do additional operations in order to see how your contract responds to real world scenarios. Another nice thing about this is you also get the various parameters. And if you're new to Tezos and you don't know how to compose them, you can just copy them out of here. There are two representations of smart contracts in Tezos. There's the Michelson, which is this, and there's a JSON interpretation of that, which is actually what you send to the RPC endpoint. We convert this into this in Consay.js, and this is actually what the trustless aspect of working with Tezos with our stack is referring to in the first slide. Consay.js is able to convert your contract from Michelson into this representation in memory on its own. Normally, the way these things work is you would convert your contract on the node, or you would use SmartPy, which is also in memory and local. But the idea that blockchains are supposed to be trustless, what we wanted to do was deliver a fully decentralized experience. You don't need to rely on a node to convert your contract, which could send you back a malicious contract potentially. And you can see this code here. So this is what the Michelson contract might look like. This is for the token. And this is what that contract looks like before it is sent to the RPC endpoint. But yes, absolutely look at how testing works in SmartPy. It's incredibly powerful. Cool, back to the TypeScript. So we may optionally deploy a token, which we're not going to do. We may optionally, well, if we deploy a token, we need to deploy a faucet because we want other people to be able to easily use our Oracle on the testnet. We need to be able to give them our tokens. So the faucet basically, it's a very simple contract that says, hey, give me some funds, and it just sends you, I forget how many tokens, but some amount. Finally, these two things. So in this example, the Oracle is a fortune cookie fortune teller. So at the bottom here, we have a handful of fortunes, and the Oracle will be serving those fortunes to whoever requests them. And that's really all it does. And then we have a client, and all the client does is says, hey, Oracle, give me my fortune. And that's it. So how does that work once we deploy these contracts? Actually, let's run them, npm run deploy. So I'm just following the steps in the documentation. So if you go to the docs, we modified the configuration according to this section. And now we're going, we did npmi before that. We go into npm run deploy. Excuse me. We described the steps. Oh, seed tokens. So seed tokens is a function that's going to use the faucet to give all of the participants of our system some balance. I think in this case, it just gives you 10 tokens. So each one, the Oracle admin is going to get some, the user is going to get some, the Oracle itself will get some, and the client contract will get some tokens. Cool. So let's do that and talk about how this works. All right, it's going to run. So this runs for a while, by the way, because we're performing multiple operations, each of which has to be completed for the next one to continue. So for example, we cannot reveal an account before it's activated. And then in the case of the Oracle admin, the account has to be fully prepared, meaning revealed, before we can deploy the token contract. And in the case of the user, we can't call a contract before the account is ready. So all this stuff has to happen in order. So this could take 5 minutes, let's say, to complete. Right, so this just sets up our system. It updates the state document with the missing information. So like here, we're going to get addresses. Here, we're going to get the secret key written in. This is obviously testnet security, right? So keep that in mind. You don't want to do this exact way necessarily in production. So then what's going to be next? Next, the client will ask the Oracle. Well, I guess let's open both of these. Next, the client will ask the Oracle for a fortune. How are we going to do that? So Oracle fee, this is an unrealistically small amount. I believe Chainlink has 18 decimal places. So this is a tiny, 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 tiny amount. Not the one you're going to be using on the mainnet. So we initialize our key store. We confirm that we have enough tokens to actually pay the fee. We get simple storage. So I mentioned earlier that contracts have state that they can store on the chain. So what this function will do is it will say, well, what is my current fortune? And after the initial deployment, if your fortune will be simply blank. How does this work? We call the Tezos node directly using the address that you got. We have the client address, which is our contract that we deployed. Storage is associated with the contract. And then the storage appears in a particular shape on the chain. We're using JSON path to parse it. This is a quick and dirty way to get your data out. If you were to look at what this actually looks like, you know what, maybe we can do that. We'll do that next time we run it. So you'll see what it looks like. And we parse out the bits that we have in place, and the thing that we're interested in is fortune. So notice, by the way, this is TypeScript, so we have types defined for this stuff. It really makes development a lot easier. Right, so we're going to look at fortune, we'll dump it in the log, and then we'll request a fortune from the Oracle. What does request fortune do? it sends a contract notification with a parameter that says, I'm calling the request fortune function, and I'm committing this payment, and I'm giving you a timeout. The timeout is the minimum duration before I can cancel the request. So if I make a request with, let's say, this is in minutes, 10-minute timeout, I would expect an Oracle to complete this request within that window, because after that I can cancel this request. And then if I do, the data provider is not going to get paid. And the data provider in this case is the Oracle. So something to keep in mind when you're servicing requests is how much time is left on a particular request if you're actually going to get the funds, because if it's too close to the end, you may not get funds. Right, and then this will terminate after requesting a fortune. The next step, let's see where we're at the deployment. It's still running, okay. So it's dumping a lot of information to the screen. If you wanted to stop that, you can just set this to error and then set debug level to error, but you guys are developers, you might want to see the details. Right, so when we run the Oracle, same thing, we initialize our keys because we're going to be calling the contract, and we get simple storage the same way we did earlier, and then we check for request. So check for request. I mentioned big maps earlier in the presentation. Let's look at what a big map is. So this is Aranex. Let me reload it. So we have a bunch of interesting stuff up front, but if you click more, you get things like map definitions. Maps on Tezos have an index. Every time you deploy a map, you just get an incremented index. The key type in this case is string, and the value type is this complex parameter. Then we have map content. So let's see, map index 37. So we can look up what map index 37 is, right? We can say filter. So 2 strings, great. And indeed, it's a string. And the key is a string. Maps, so these are hash tables basically, right? So the key is not stored directly. The key is stored as a hash. We, in the indexer, pull out the value when you call the contract to store the data. So that's how we know where it is. This is the operation where that modification happened. And these are big maps, essentially. And then there's also a collection of map owners. So this contract owns map 104, this contract owns map 103, and so forth. It is possible for one contract to own multiple maps, and the Oracle contract we're deploying actually does. How is that going? That appears to have completed successfully. So in that case, our state will have stuff in it. So we deployed an Oracle contract. Let's switch to CarthageNet. And here's our Oracle contract. And it does indeed have 2 big maps. So we're mapping a number to some complex thing. And here we're mapping some complex thing to a number. This is just a reverse lookup table. Excellent. So we deployed our contracts. Now we can call them. So we're going to do npm run client. And again, this is simply going to request a new fortune. So let's see. Current fortune, blank. Excellent. So this is going to take a brief amount of time to confirm on the chain. And let's see, by the way, Oracle user Alice is this address. So we can go to Aranex on CarthageNet. Operations. Source. And here are the transactions that Alice is performing. Excellent. We can also, by the way, take a look at contract calls that we're receiving. So the Oracle would have received a ping. So we're going to change this to destination. Here, we have received a call from the client contract. Cool. So now let's request a fortune. So now we can service this request by running npm run Oracle. Right. So how does this work? What we do is we index the requests in the Oracle that are pending. So we need to see if there is a key that's available. Big map interactions are a little bit complex in Tezos. So we know that request ID is what we're going to be packaging. We know it's a NAT. We know that because we just looked at the contract definition. Then we will get the payload of that operation. Now, we're going to process this request regardless of any conditions, right? So we don't care how much money we're getting paid. We don't care who the client is. We don't care what the timeout is. We're just going to process it, right? So process request will take a random fortune out of the 5 that we have written down, and then it will call itself to fulfill the request. And the contract internally says, oh, I'm fulfilling request ID, whatever, with this payload. And this payload is dynamic. It could be anything you want. It supports 3 data types, numbers. So in Tezos, there are a few different kinds of numbers. There's nat, a natural number, and there's int. So natural numbers are greater than 0. I'm sorry, 0 or greater. Int can be negative. In this case, we're using string. If you're looking to submit a more complex parameter, you can do that by encoding it in binary, and then you can send whatever you want. It doesn't even have to be parsable by the chain. Great, so then we're going to call the contract. So let's do that. And this is, again, going to run for a little bit, and it's going to dump a bunch of stuff to the log. But ultimately, what we're going to do after this is finished is we'll run the client again to confirm that we have received a fortune. This will take a second. So what you're seeing, by the way, is we have this feature in Consay.js. You can await operation confirmation. So we know which group ID we're looking for. This is just the operation hash. And we're going to wait for 10 blocks. And the block time is at 31 seconds that we mentioned earlier. And yeah, so this is just waiting for that operation to appear on chain. And once it does, the application will exit. And we're done. So let's run client again, which, by the way, will again, of course, submit another request. But what we want to see is that our fortune has changed. There we go. Ominous. Now we can also confirm this on Airnex. So let's grab our client address again. And in storage, we indeed have our fortune. We can copy that out. There you go. Cool. So this is the demo. The code, as you can see, runs. This is us in various places. I'm also on the Hackathon Discord channel. I'm Cryptonomic there. I think all of these links are in the README for the project as well. So yeah, thank you for listening. I think, let's see, we have a few minutes for questions, if you have questions. Pat, I don't know if you're going to be unmuting people for this or not.
Can you see the questions there in the Q&A?
Yes, so let's see. How do you make a Tezos smart contract request related to job ID? So job ID is a parameter. If you look at the service request function, job ID appears there. We're just ignoring it. But you're right. If you were building an Oracle that is going to service multiple kinds of requests, you would use job ID to decide how to respond to a particular request.
There's a couple questions on the YouTube as well. How does typing translate from Python to Michelson?
Smart Pie Magic. Basically, what they're doing is that they're looking at, well, so there are two ways. One, there is a Smart Pie feature that allows you to explicitly define a type. You can say something like, I honestly don't remember the syntax off the top of my head, but there's a function call for that. You can define a type explicitly and assign it to a particular variable. Otherwise, when you define tests, and each one of your entry points must have a test associated with it. I mean, it's for your own good, to be honest, but that's a requirement. This test, you are providing static values into it, and static values are, they can be, the type can be inferred, right? So if you pass a number, it's a number. If you pass a string, it's a string, and so on. If it's ambiguous, then you have to specifically say what kind of data you're passing in.
Cool. And then the last question here. Could you please explain Lambda storage?
Right. So storage is defined with a type the same way that you defined an entry point. Entry points are functions on smart contracts on Tezos. So you can say that I'm going to be storing a Lambda that accepts some collection of parameters. And these parameters are typed, of course. And then you can have a function in your contract that says, I will take this Lambda and store it in storage. And then you can have yet another function that will execute that Lambda out of storage by perhaps passing it some parameters that the user passed into this entry point. So some people call this contract upgradability. Again, I think there's a lot of danger here with that feature. I would not want to use contracts that execute Lambda out of storage, especially Lambda that's modifiable. What I mean is it's possible to store a Lambda in a contract on deployment, and then its Lambda is never going to be modified. So it's basically as if you wrote the code directly into the contract itself. I don't know why you would do that, but you could do that. I think it might cost you a little bit more than to just deploy the contract directly. But if you deploy a contract that allows you to modify this Lambda, even if it's just administrator, even if it's a multi-sig administrator, it still provides a path for the contract to execute differently from the way it was originally deployed. And that reduces trust. So I would not do that. But yes, it is possible to store Lambdas.
And then it looks like we have time for one more question, which is there are there Solidity compilers too?
No. So Solidity is a fundamentally different language from Michelson. I believe there are efforts to convert Solidity into Michelson. I don't know where they're at. I would say that there are enough architectural differences between Solidity and Michelson that you really don't want to be doing this. I would personally understand how, let's say, Smart Pie works. Like, I would not necessarily recommend that you learn Michelson, especially on such short notice, but Smart Pie is pretty easy to work with. And it uses a commonly visible syntax, like you can do this. Be careful when you're converting Solidity directly to Smart Pi, let's say, because again, for example, there are no return values. You really need to keep a bunch of these things in mind when you do this.
Awesome. Well, thank you everybody so much for coming. This has been a really, really helpful workshop, and I hope to see some really cool projects for the hackathon that's going on here, built with some of the tools that you've learned from this workshop. So, Mike, I want to thank you so much for being here. This was fantastic, and good luck everybody on the hackathon.
Thank you for having me.
All right.
Yes. Thank you very much, guys. Bye-bye.